Okay, let's start. No.
Okay, sorry for being late. So let's start today's seminar. Today's speaker is Professor Chengcheng Han from Yat-Sen
Yeah.
University. He'll talk about type II Seesaw leptogenesis. Please start when you're ready.
Okay. First of all, I should thank Myung-Hoon and Professor Ng for inviting me to give a seminar here. And yeah, I'm very happy to come back to this place again. Everything is familiar, and I'm very happy. And today I will talk about my work last year about this type II seesaw leptogenesis. I will explain later. And yeah, okay, let me start. Okay, it works. Yeah, as we all know, standard model is very successful to explain many of the low energy physics. But we have many motivations to extend the standard model, and here I list some of them. For example, the inflation, which particle drives the inflation, and how the neutrino gets mass, and why we have the baryon asymmetry or universe, and other dark matter. Maybe some multi mass 2 or W mass, but as far as I know, today they will announce some news about multi-mass 2. Maybe you can wait and see. Yeah, we have many motivations. Here I will talk about these three problems. Okay, let me give a brief introduction of this inflation. Inflation is the early stage of the universe. In a very short time, the universe expands very fast, and it can solve some problems. But to me, I think the most important thing is inflation, just stretching this quantum fluctuation to a very large scale. Then in the CMB, we can observe some temperature fluctuations, and if we have a dark matter, then all the fluctuations will become the large scale structure or universe. That's why we can live here. When people talk about the inflation, usually they assume some scalar field takes some value in the early universe, and the most popular framework is the slow roll inflation, which is a scalar field follows such dynamics, and this h is the Hubble parameter, and if we have this slow roll condition, then we almost will get a constant Hubble parameter. Then in a short time, the scale factor of the universe is exponentially increased, and yeah, this simple framework can explain this the origin of the inflation. And but indeed we have some observations. One of the things is the fluctuation, which is if we use the slow roll inflation, it has something to do with the epsilon parameter. And as far as we know, this is order of 10 to minus 9, which is shown here. And although not only the fluctuation, the value of the fluctuation with the scale factor. So how much the fluctuation change, we can also measure. And from the slow roll inflation, we can predict this fluctuation should be close to its scale invariant. But indeed, the measurement prefer this observation. And the other thing is, except the scalar perturbation, they also have the tensor perturbation, which usually people use this tensor to scalar ratio R. But currently we don't observe any this primordial gravitational wave, and that's some upper limit for this R. And you can check this K is the scale factor, you can see, and this is the fluctuation. This range is what we will measure. I think almost 2 orders range we can measure very precisely. And although this is the current observation, this is the ns. If this is equal to 1, it will become totally skew invariant. But from the slow inflation, we know it's not exactly skew invariant. So it has some deviation, and which you can see. And also the tensor to scalar ratio, that's the upper limit. And you can roughly check what kind of models is preferred. And here I want to mention if the way proportional to phi square, which is people are always use is this quadratic potential. It actually is not preferred. I guess where this I guess is here or somewhere. Yeah, you can check this. This kind of potential seems not consistent with observation. Yeah, we don't know why it is. But in this kind of models, they predict too large R, which is not preferred. Yeah, so inflation seems not so easy. Okay, then the other problem is the neutrino mass. We know neutrino has a mass, and we need to explain the neutrino oscillations. And we already measured even the mixing angle of these three neutrinos and also the mass splitting of them. But yeah, the root value of the neutrino mass we don't know. But at least we know that must be one neutrino mass which is larger or similar to 0.05 eV. So neutrino must be massive. That's from these two relations we can get to this. And but if we see the neutrino mass, we will find this is much smaller than the other fermion mass. Then we may guess the neutrino mass get a different mechanism, get different from the other particles. And yeah, well, the most popular model, not this is not the only model. The most popular model is the Seesaw model, which they can generate the neutrino mass at the tree level. And yeah, the most the popular one is if we add three red-hand neutrinos, then we can naturally have the neutrino mass. And this is the if you know this Weinberg operator. This is how they generated the Weinberg operator. And for type 2 seesaw, they didn't add some fermions. They add one triplet Higgs. It's a triplet, the SU2 triplet scalar. And here that's a one. They need a one. But here they need at least two. So in some sense, this is also very simple framework. Here I will talk about this model. And type 3 is they need at least 2 or 3 triplet fermions. Seems a little bit complicated. And yeah, different from these two. This is a scalar particle, which is very important to use the property. It is a scalar. And here, this is a type 1 seesaw. Everyone may be familiar with. We just add right-hand neutrino, and then from the diagonal, this mass matrix, we get the neutrino mass is suppressed by this right-hand neutrino mass. But for type 2 seesaw, the structure is a little bit different. If we add the triplet Higgs with a hypercharge 1, then we can have the coupling directly coupled to this delta. This is similar to Yukawa sector or standard model. If we add the delta, we must have this coupling. And this, because delta is a triplet, we can write down it like this. And that's a neutral one, delta 0. And if we have this coupling, it will predict we have such kind of coupling, delta 0 coupled to this neutrino. If the delta 0 gets the vacuum values, then neutrino gets the mass, similar to standard model other fermions. One Higgs gets vacuum and the other particle gets mass. And yeah, this is also, I think this is a very simple idea, you know. And yeah, this not only gives the neutrino mass, at the same time, the delta also get the lepton number -2 because coupled to lepton, but this is C here. So the lepton number is -2 for delta.
So it is Hooke's clock.
No, because the charge assignment it cannot directly couple to quark because the hypercharge. You cannot manage to cancellation of the hypercharge. Yeah, and if we check the potential, it becomes more complicated than standard model. But anyway, we should write down the general potential for delta H, and you can easily figure out this delta dagger, delta H, dagger H. But there's some additional terms which is, for example, this term is also allowed. But more importantly, they have something like this term. Because the Higgs is really similar to the L in some sense, then Higgs can also couple the delta. But this operator is dimension 3, and the mu parameter here is dimension 4. And because Higgs have no lepton charge, and this term will break the U1L, global U1L symmetry. Because delta has the -2 lepton charge. And because of this term, that's why neutrino will get mass, because we must break the lepton symmetry. This is the origin of the breaking of the lepton symmetry. And you can you can imagine if there's no such term, we don't have neutrino mass. Yes, indeed, the vacuum value of the delta naught is proportional to this mu term. Yeah, if the mu term is there, then we will have the neutrino mass. That's very, very natural. I think this term is allowed, and the neutrino get the mass. But from the electroweak precision measurement, the vacuum value of the delta should not be too large because it's a triplet. It will change some row parameters, and then the limit on this vacuum value should be smaller than GeV. But it must be larger than this 0.5, this 0.05 EV. Why? This is because we want to explain neutrino mass. At least one neutrino mass has this mass. If we don't want the Yukawa coupling too large, then we have this. Actually, this is almost 10 orders magnitude, 10 orders range for this vacuum value, and we don't know where it is. So it is 10 orders. Okay. There's no problem for this type 2. Yeah. What?
A very nice question. You say that it's trilinear scalar interaction breaks the U1 asymmetry.
Yeah, this.
But in the previous slide, when you write on the power interaction.
Yes.
The last slide.
There's something wrong.
In your hand.
Okay.
Here is LCR delta L.
Yeah, this
Delta
is.
is a wave. This also breaks asymmetry.
Oh, you mean if this get a vacuum value, it will. It will spontaneously break the L symmetry. Yeah, but this term, indeed, they don't break the lepton symmetry. If delta get the lepton number, indeed, it gets a vacuum value, it will spontaneously break L symmetry. Yeah, you are right. But if we have no such term, it will not get the vacuum value. So it is consistent, right? Okay, and neutrino mass sometimes can connect to another problem of the baryon symmetry of universe. And I don't want to explain more about this. We have two observations. One is from BBN, one is from CMB. We can infer from the ratio of the baryon number over the entropy or the baryon number over the photon number, which is order of 10 to -10. So actually these are two problems related. One is why there are more baryons than antibaryon. And the other problem is why the difference is so small compared to the photon number. Yeah, this contains two problems. And if we imagine this world have no baryon symmetry, say it's like a dark matter, they annihilate, and finally the baryon number equal to anti-baryon number, and the ratio to the photon number is 10 to minus 20. Then, if in this case, our universe may have different baryon and anti-baryon region, but it must be very rare, because this is 10 orders smaller than this. Then I guess we cannot be here. Yeah, that's why the baryon symmetry is very important. Yeah, like the dark matter. If we have a symmetry, we stop the annihilation of the proton and the antiproton. Okay, to address this baryon symmetry, a long time ago, Sahara already gives the three conditions. They need a baryon. Here it should be changed in the baryon or lepton number variation, and C and CP variation, and the most important, the autothermal equilibrium. And you need the standard model has the condition 1 and 2, but the CP variation is very small. And the third condition, they don't satisfy, because in standard model we could have two processes which have the have this first order phase transition, which is the QCD phase transition or electroweak phase transition. But according to recent study, the QCD phase transition must be crossed over, and although the standard model electroweak phase transition is also crossover, then the third condition cannot be satisfied. Then to generate the baryon symmetry, here I list three popular ways. One is the electroweak baryogenesis, because they need the first order phase transition. Then many people, which is very popular recent years, many people are thinking to add a new scalar to standard model, then they can trigger this first order phase transition. Yeah, why this is popular? Because when we have the first order phase transition, we have the gravitational waves. This is what they want, but this is not sometimes not a good motivation if we just want a gravitational wave. If we want to have the baryogenesis, most of the models they need additional CP variation, but they never mention it, and they didn't. Most of the papers they didn't calculate this how much baryon symmetry is generated. But anyway, this is one of the very popular models people are doing these days. And the other is I think this leptogenesis, which I call this thermal leptogenesis from the Bulgaria and long time ago. And in this model, they have the right-hand neutrino, and they can generate the lepton symmetry. Then the final baryon symmetry can be transferred from the lepton symmetry. This relation is just this, and this B is the initial baryon symmetry, and L is the initial lepton symmetry. So if we want to generate this, we need the anti-lepton symmetry actually. So we need to generate many anti-leptons, then we can have the baryon symmetry. And the other one is the long time ago, even 1 year earlier, than Yat-Sen's work, and this is from like a dime mechanism. This is from these two authors. But this mechanism is very popular in people who studying supersymmetry. But many people who don't study supersymmetry, they never heard about this. But here I will explain why supersymmetry is a very natural framework for this. But in my model, I don't need a supersymmetry. Okay, for the type 1 seesaw leptogenesis, and this is very cited, and many people are following this works. If they have says at least two right-hand neutrinos, and then in the early time, right-hand neutrino will decouple like the dark matter decouple, but later it will decay. But if we have the tree-level diagram and the loop diagram, then the decay of the right-hand neutrino is different. It can decay to lepton and anti-lepton, but the decay rate could be different if we have these two diagrams. And then we have some rate, so how much difference of the lepton and the anti-lepton. Then if we have enough of the right-hand neutrinos, then we generate the lepton symmetry first. Then from this formula, it will give the baryon symmetry. That's why people call this the leptogenesis. But leptogenesis is also means baryon genesis, but have a different way to do this. But in a very natural model of this kind of model, they generally require the right-hand neutrino mass is heavier than 10 to 7 GeV, which is very hard to test. But it is very good, but very difficult to test. But if we have, but some people argue if we have very small splitting about these two right-hand neutrinos, then they can enhance the lepton symmetry and yeah, the mass can be smaller. Yeah, these days many people study this special scenario. The mass splitting is very, very tiny, which is not natural, I think. Okay, how about the type II Seesaw leptogenesis? This is also very interesting because we only add one triplet Higgs, we explain neutrino mass. If we can explain the baryon symmetry, it will be very interesting. And yeah, the earliest work is from Ernest Ma a long time ago in 1998, and it's also very well cited. So it means this is a very interesting work. And they also try to this tree level and loop level diagram, and but they find one triplet Higgs cannot do it. Yeah, you can check this formula. They need the mutant. Mutant is the coupling of the delta to Higgs. This mu1, mu2 star. Then if they only have one triplet Higgs, then the complex part cancel. Then we cannot have the lepton symmetry generated by the triplet Higgs. That's why in his paper they call this heavy Higgs triplet. They don't call the type II Seesaw leptogenesis because they need two triplet Higgs to do such kind of thing, which is not good. One is enough for neutrino mass. Two, then it's not the minimal model of the type II Seesaw. Okay, then in last year we completed this thing, and because in the beginning we used something titled like diamond leptogenesis from Higgs inflation, and here in the start of the paper we claim one of the triplet Higgs is enough to generate the lepton symmetry, and later on we write down a longer version of the paper. We just use the name type II Seesaw leptogenesis. Yeah, I will explain how this idea works. And here, actually, we didn't use thermal leptogenesis. We use this like a dam mechanism. And let me give a brief introduction of this kind of mechanism. If we have some complex field that takes the baryon or lepton charge, then we can write down this kind of potential. And we have the U1 conserving terms like this. And if we have a small U1 breaking term, assuming this is the U1 breaking term, but it will be very small. Then from the current of the baryon current, we have this relation with the phi. But if assume phi is spatially constant, yes, yeah, then the number density of baryon have the relation you can just compare, and have the relation with the phi dot. if the phi dot is non-vanishing, it maybe generate the baryon symmetry. But if we use this polar representation, then it's proportional to the theta dot. Well, what does it mean? It means if in the this is the real, this is the complex part. Then if it rotates in the phase space, then the baryon number is generated, is non-vanishing. This is the key point of this mechanism. And if you calculate the motion of the baryon number, you will find that it has something to do with this term. This term is original from the U1 breaking term. So that's why we need a small U1 breaking term. Yeah, this will generally generate this baryon symmetry. But we need some three conditions, which is very not easy to satisfy. First, we need a scalar particle taking the V or L charge. This is very difficult. If you randomly add a particle, it must be coupled to the lepton sector or the quark sector. Yeah, and this B and L violation terms must be there, and then this particle must be charged neutral. If you have a lepton quark, you can couple to lepton and quark, and then it takes B and L charge, but it must be not charged neutral. It's not easy. And although the third condition is the scalar particle have some initial, initially they are non-vanishing, but finally they can go to this small part, but in the beginning it must be non-vanishing. This is although not the easy condition, yeah. Here I will explain one example which can satisfy these three conditions. This example is from supersymmetry. Why is supersymmetry is very natural? Because all the fermions, quarks, leptons naturally takes the V or lepton charge. This is this is because we have all the fermions has their scalar partners. And more importantly, in supersymmetry, we have a concept called the flat direction. Flat direction means if SUSY is exact, then the potential in particular direction is totally vanishing. It's like something like I don't know. Yeah, if you have two fields, phi1 and phi2, and in some particular direction, I'm not sure. In this direction, the potential is totally vanishing. That's what we call this flat. But anyway, if we add some SUSY breaking term, we will have small potential along these directions. Yeah, and this long time ago studied by the Michael Dunn and Lisa Randall, and they write down all the flat directions in supersymmetry. But only this kind of flat direction can be used to generate, because we need the non-vanishing B minus L symmetry. Yeah. Then in this kind, all this flat direction can generate the baryon symmetry. And here I give one example. Well, if we choose this, then the flat direction is along this. If we have non-vanishing value in here and here, then the potential disappear. But we still have some SUSY breaking term which have this mass term and all the small U1 breaking term. Here this M actually is the scale for the generation of the neutrino mass. Okay, in this case we can actually have this flag down mechanism. So another thing I forgot to talk is, if this direction is flat, then it can easily get a large vacuum value in the early universe, because we have the inflation, it just fluctuates and finally get a very large value. So this flat direction is very important to realize this idea. But however, in my model, I don't want to use SUSY. Yeah, SUSY is good, but I don't. It's not a simple type of SUSY. So if we add a SUSY, we have many more particles. And yeah, let us thinking about the three conditions for this mechanism. First, do we have a scalar particle taking the V or L charge? Yes, indeed, this delta takes -2 lepton charge. Second condition, do we have the V or L violation term in the potential? Yes, indeed, I mentioned it. Because the violation term, we have the vacuum value and we could generate a neutrino mass. So it must be there to explain neutrino mass. How about the third condition? Because we don't have flat direction, we don't want to use SUSY. So how we satisfy this third condition? And the answer is very simple. If this particle plays a role in photon, then we have the initial vacuum because it must explain the inflation. It must have a large value. Then these three conditions can be naturally satisfied in this model. Okay, yeah, all the motivation, all the Up to now, everything is just go to calculation, and we have already have everything. Just identify the parameter space. Yeah, as I mentioned, this kind of potential is not consistent with observation, and we can easily fix this problem if we use the idea of the Higgs inflation. I guess you already listened to my talks from Chengcheng Park about this Higgs inflation. If we add the non-minimal coupling to R, then we can make the potential to be flat, and then we can explain the data of the inflation. Here we do this. I don't want to talk too detail about this Higgs inflation. I assume you already know this very well. And here, similar to the Higgs inflation, we also add the non-minimal couplings, which is we only use because we have two fields. We need to add the Higgs field and the delta field. This is two non-minimal coupling. This is very, very natural because we have two scalar particles. And then we have the potential and the Yukawa terms, and everything is here. But here there's something difficulty because we have two non-minimal couplings, and the inflation becomes very complicated to calculate. Fortunately, I know the Heyman Lee's paper, and long time ago he studied if we have two fields and both have non-minimal coupling, what is the dynamics of the inflation? And in this paper he found, okay, in this model it's not so difficult, and the inflation the inflation is also very simple because it will happen at some particular direction. Yeah, it's not in this. It's not complicated. It just follow one direction, and there's an angle in this direction depend on the lambda coupling and this non-minimal coupling. Then you can really change this kind of direction. Yeah, according to their calculation, and indeed, we also check this result if we use the two-field inflation, and it really follow this particular direction. So the inflation part becomes very simple in this model, and similar to SUSY case, but here we have a general angle, could be any direction, depends on our parameters. Okay, then our inflation model is just becomes one. We assume this direction is one of the field. Then all the calculation we can use the analytic calculation now. Then we just use everything just one field, and we change some relation. For example, the Higgs has this zen alpha and that has the cosine alpha thing, and we have everything. Here we add the general potential for this term, and this cubic term, and also we need to add the dimension 5 operator term because during inflation the field value is close to Planck. This dimension value operators are not small anymore. But anyway, in low-end physics, this does not matter because the Planck is suppressed. Yeah.
Is this by a linear combination of delta and H?
Yes, yes. Linear. That's the angle. Not very complicated. Thanks to Hamming. Okay, now we need to keep the data dot from here. Data dot, from the delta term to generate the lepton symmetry. Then we have the phi field and theta dot. If this is non-vanishing, then we have the lepton symmetry. Now we just one field to calculate how much value about the lepton symmetry. Yeah, here I give one of the results. This is the time if we start from here, and this is the lepton symmetry. In the beginning, theta dot is vanishing, but anyway, when we start from inflation, the theta dot will also follow slow rule. Then suddenly, the lepton number becomes non-vanishing. During inflation, it will continually generate. But after inflation, here is the during inflation, here is the after inflation. Then after inflation, the lepton number will just redshift by the scale factor A. So that's why it will just become small and small. Here, almost all the lepton number is generated during inflation. Yeah, this here I just roughly give some parameters. Okay, the conclusion is lepton number is generated during inflation. After inflation, it just conserved and redshift. Okay, to get the number of the exact lepton number, and for example, in the Higgs inflation model, the reheating temperature is roughly 10 to 14 GeV, and use this temperature, we find that if we want to explain exactly the baryon symmetry of the universe, we need the dimension 5 operator, which is 10 to minus 15. It must be very small. If it's too large, it will generate too many lepton number. Yeah. Okay. And we need to also consider the after reheating, the delta and the Higgs is in the thermal bath, and for example, this trilinear term, this cubic term will also break the U1L symmetry. If it's too large, then all the lepton number is generated will be washed out. So basically, we need a very small mu term. On the other hand, we have also the 2-to-2 process, which is also can wash out the lepton symmetry. Then we get the upper limit for this triplet Higgs to be smaller than 10 to 12 GeV, which is good for us. Okay, here later I will show what is the constraint, but this prefer a small mu term. Oh, okay, this is our final result, and this is the mass of the triplet Higgs. It can, as low as TeV. We can really directly test it. And this is the mu term, which is the cubic term. It must be small. All this blue reading is because the lepton number is washed out. Then we have we only have this reading. This black reading is because the vacuum value of delta becomes, because the vacuum value has something to do with mu. If this is too small, then the vacuum value is becoming too small. We cannot explain neutrino mass anymore. So we need to cut this region, but fortunately we still have some region which we can explain everything. Yeah. And you can check this red line. This I give the Yukawa coupling and also the vacuum value. Yeah, we find this vacuum value that should be smaller than 10 keV. Please remember one of my slide. I show the vacuum value can be as large as GeV. So it is 10 orders. Now I cut it 10 keV and 0.5 eV. So I cut maybe 5 or 6 orders. The region is not allowed by my mechanism. Yeah. Yeah, and the good thing is it can be as light as TeV or 100 TeV. Yeah. Then we have plenty of region we can check. Yeah. This here I plotted the 100 TeV collider and also some lepton flavor variation test. And this region is excluded and this is future reading. Yeah, I don't know how much time I used because later is all the phenomenology.
So it's now 10:50, 50, but I mean you can use
Okay,
as much
okay.
as you want.
Okay, I can share. I can save the time, or I can talk more. Yeah, let me talk about the phenomenology, the model. Okay. Yeah, to study the collider physics. Yeah, people already study because this model contains a doubly charged Higgs. Then the decay of such Higgs depends on the vacuum value. Yeah, it's from 1 GeV to 10 to minus 10 GeV. Yeah, this range we can explain neutrino mass, but depending on the vacuum value, it can decay to 2W boson, or it can decay to same than lepton. But according to our model, it only can be in this range. So it will only decay to 2 leptons. This is a very good signal for collider search. 2 things than leptons associated with the doubly charged Higgs. And actually, the LHC already performed that kind of research. And if this decay rate is 100%, the current limit is around 800
So
TeV.
how this guy is produced?
Yeah, from this Julian process, because it's doubly charged, just from C and gamma, and you have. I don't know. Can you see this? Yeah. Then this will decay to the same lepton, and the background is almost free. This signal is very, very clear, and that's Alex can do. I think the current search they are not fully explored the sensitivity. They just have the roughly search. I guess if we have developed some method, then they can do more. They can do better. Yeah, and this is some people do this is 100 TeV collider. They can reach around 4 TeV at 5 sigma. Yeah, the smoking gun is if we observe this doubly charged Higgs from the lepton decay channel, it will have
Can you go
something.
back to this mass splitting plot?
Yes.
Yes.
Yeah, the mass splitting is about this one and this one. But later on, we have a calculation. Though the mass splitting should not be too large. It has this.
How about the mass split between the charged one and neutral one?
Oh, it's similar because they are from same parameters. Yeah, they are almost close to each other. If that's one of the quartic coupling beside the splitting of these 3 particles. But because this quartic coupling cannot be too large, then the mass splitting of these 3 are very tiny. Yeah, from our study, it should be smaller than 5 GeV. Yeah, so basically it will decay to leptons. And although it can also predict some lepton flavor variation process, for example, this, Yeah, where we have such coupling because we need to couple to neutrino, and then all the Yukawa is almost decided by the neutrino physics. Then we don't have much free choice. Then it must couple to all this non-diagonal coupling to lepton sector. Then we must have a lepton whatever variation. Yeah, that's why we draw this exclusion gradient. And yeah, for the neutrino physics, because we don't have the right-hand neutrino, so it must be Majorana type. And then we expect the future this neutrino, this double Vela decay can give the indication of this kind of model. And yeah, in addition, one of the things is interesting is the CP variation in the neutrino sector. But current measurement from T to K prefer non-vanishing CP variation. But no one result, they are consistent with no CP variation. So we don't know which is correct. But what I want to mention is our model has nothing to do with CP variation because CP variation is happen at the early universe. So basically, if we don't observe any CP variation, maybe it supports our model. But if we observe CP variation, it's okay. Nothing different. Okay, and also some cosmology signals. For example, we have some prediction of the inflation, and because it's two field, we have some non-Gaussian signature, although some isocurvature signature, and although some gravitational wave, which we need to calculate. Yeah. Okay, this is a summary. Yeah, we have one of the model. We just add one particle. We explain 3 problems, and there's so many signatures. So we can check this model. Okay, that's all.
Thank you very much for the nice talk. Any question?
Yeah.
So since you said you need reading temperature 10 to the power 14 GeV.
I don't need. I just set the paper from inflation. They say that this heating temperature is around this region.
No, this is not for your model.
Yeah, it's not for my model, but because the calculation is very complicated, and we just roughly because we all heating is all similar because we have triplet Higgs and doublet Higgs. Then it will be change a little bit.
But because because this model, this typical values are for large scale models, large scale inflationary models.
Yeah.
If you have 10 to the power 14 GeV, then your energy scale will be higher. The inflationary energy scale will be higher than this. But then your tensor to scale ratio will be, I guess, will not be within the current Planck result.
Oh, it's okay because
all these models, if what you mentioned,
no, yeah,
before the Planck result.
Okay. Yeah. You are talking about all this model is not preferred, but Higgs inflation.
No, yeah, I know Higgs inflation, but this value of 10 to the power 14 GeV, if reading temperature is this high, then inflationary scale will be higher.
Yeah, inflation scale is 10 to, I guess 10 to 16.
Yeah, but these are for, this was are now ruled out.
No, it's totally fine. Yeah, because this Higgs inflation, this idea in the high large value, it becomes flat. Yeah, we check.
And if you have like 2 non-minimal coupling and 2 fields,
yes.
So will your this isocurvature perturbations will be small?
Yeah, we calculate it is small. Yeah, thank you. Yeah, in our paper we even the referee says that, and it takes me many time to calculate this isocurvature, but it is okay.
Thank you.
So in your model, so what determines the total lepton number? So could you go to the page 31 or?
I think yeah. Here I guess it will Here,
Yeah, this n.
this parameter determines the lepton number.
So you mean NLN is determined by lambda 5 children?
Yes, yes. And also the initial theta, because we don't know where it is. It could be anywhere. Yeah.
I think so. This NL also depends on the shape of the potential in general.
Oh, but it's almost fixed. Yeah, you mean it depends on this lambda something? Yeah, yeah. Here, yeah.
Potential.
We can use the lambda for different. Yeah,
Okay.
we fix the lambda. But if you change the lambda, yes, it will change a little bit. It depends on. Yeah, I guess say lambda and lambda 5. These three parameters.
So here lambda is the combination of lambda h and lambda delta, right?
Yes, it is the effective lambda. All right.
Lambda.
Because we have this relation, we can transfer all the different lambdas. There's too many lambdas, and they combine together.
And it seems that your choice of lambda is very, very small.
Oh,
But you don't care because you are talking about the Planck scale physics. In the low energy, so lambda can be order 0.1.
Yeah. Actually, why we choose this small lambda? Because we want to avoid the discussion of the preheating will be too violate or something. But in principle, our mechanism has nothing to do with the value of lambda. We just need it to work. But we try to avoid. People may say, "Oh, your preheating is too strong," or something. We try to avoid people complain this part. But basically, our mechanism still work if lambda is all one. No problem. But we need a much larger C in this case.
So you haven't checked the RG.
Later on, we checked. Yeah. I have one paper with my students. We check all the RG running of the lambdas.
Yeah, because anyway, we know there are experimental values in the low energy.
Yeah.
And if we know RG, so we can calculate the lambda.
Yeah, but we don't have this input.
Okay.
Yeah, and the good thing is the Higgs instability can also solve that because we have different lambda contribute to the RG running of the Higgs jet coupling.
Any other question?
Yeah, I
Sure.
have a question.
Yes.
So I have two questions actually. One about this mu value. You said the mu value should be low, right? Can you just repeat the argument?
Oh, yeah. Here.
Yeah. So
Yeah.
how low you need for you? Mhm.
See, it's rather low. It's very small.
Mhm.
It's less than 1 GeV.
Less than 1 GB. Okay. So this is consistent with obviously probably you can fix the neutrino mass and mixing with this value. So that is probably fine, right?
Yeah. But fortunately, we have this middle region exists.
And there is another question related to this. So people who tried electroweak baryogenesis, they studied this this type 2 seesaw for first order phase transition, and that gives a large quartic coupling, and which is not consistent with Higgs to gamma gamma.
Oh, yeah.
So,
I
yeah.
agree. This we can do if we are the triplet Higgs, we can do the first order phase transition, but they need the triplet Higgs. I think less than 500 GeV. This is not good. Some kind of collider search already almost exclude such a possibility.
Yes. But from the leptogenesis point of view, there is no such constraint, right? This is what you are saying.
Yeah. Yes.
Okay. Thank you.
Thank you for your question. Yeah, Carlson.
So, yes. What is the origin of lambda 5?
Oh, it's a dimension 5 operators, Planck suppressed. We need to add this because here is
You just include the baryon?
yeah. Planck suppressed. Planck suppressed the operator here. Because this value is close to Planck, then dimension 5 operator can be important.
And that under 5 tilde is the source of the lepton.
Yes. Planck suppressed the operator do the important role.
So it has nothing to do with the neutron.
Oh, yeah, we try to use it will be good if we use mutual. Yeah, we tried this, but the problem is we don't understand the result. I don't know how to treat this because if we have the mutual dominate, then the lepton number will oscillate, and we don't know how to. It does not mean it's wrong, so we cannot understand how we calculate the final lepton number, and we are still discussing these problems.
So I mean, so even if you ignore the gravity, you need the lepton.
You mean yeah? This term we need.
That's a real source of the lepton.
Yeah, in this case, this is the lepton number is very simple. But if we use the mu term, as we read in the paper,
My question is this: in the definition of type II Seesaw,
yeah,
at renormalizable level, you don't have lambda 5 theta.
yeah, you're right.
So when to have leptogenesis a la upright line with Higgs inflation from combination of Higgs and alpha, you have to add
The problem, yes, I have, yes, you're right. I need the Planck suppressed operator.
so you don't care about the origin. You don't ask about the origin of this lambda 5 theta.
No, we don't know how it happens, but it's. I assume it must be there because it's Planck.
Yeah, in principle.
Yeah.
So it's not under control. It has nothing to do with your. I mean,
Yeah, it should be some kind of not to be too large.
so I mean, using the leptogenesis, there is some connection between leptogenesis and neutrinoless and everything in the single model. Right?
Yes.
But, this lambda 5 tilde
Oh, it's
doesn't affect the neutrino phenomenology.
no, because it's Planck suppressed. Small, yeah. Yeah, and yeah, you have a good point. Yeah, if we use the mutable to do everything, it will be very happy. Yeah, but it does not mean mutable cannot do that. It doesn't mean we don't understand the result.
You assume simply, I mean, in addition to the usual renormalizable Gaussian Planck scale suppressed lepton number violating operator.
Yes,
That's what you are assuming.
yes.
When Dr. goes a baryon number violating operator too.
Yeah, we assume the Planck.
Another question is, you have a doubly charged scalar.
Yes.
Then, I mean, so mu is small, but did you estimate the UNG minus 2 in your model?
Oh, I think it does. I think it is small because it should be beyond 1 TeV and because it is heavy, it must be very heavy.
Fifth order of TeV.
Yes, TeV. Yeah, maybe it has something to do with the W mass. Some people argue for this model.
And plus going to U plus and V plus.
Yeah, it can go to
That's coming from
E plus, E max.
from the Yukawa.
Yeah, then you can, yeah. From the Yukawa, we can calculate all the decay channels, and the Yukawa is totally determined by the neutrino physics. Then everything is predictable,
Another.
Yeah, can I ask one more question?
Yes.
Since you are generating the leptons during inflation, so will not this have any effect on the CMB and isotropies? Or how do you control this? What is the handle of this effect?
Well, what do you mean?
I mean, your lepton is generated during inflation,
Oh,
so will
No.
not that have any effect on the CMB and isotropies?
I think it does not have much effect. The lepton number is generated, but it will release the lepton number after reheating. Then all the calculation is, if you familiar with the Higgs inflation, everything is the standard. That's no problem. And we just need to tune these two couplings to satisfy this. Then we have the proper, everything is from Higgs inflation, and we can fit the inflation very well. I guess this.
For your attention. If not, let's thank speaker again. Thank you very much.
Thank you. Please.